Hello, everybody. My name is Jakub Schmiegel, and I work at Intel as a software engineer. And today, I'm going to present a Redis operation with persistent memory. So, for many years, computer applications organize their data between two levels. The memory and the storage. So we believe that emerging technology, which is a persistent memory, will introduce third level, which can be accessed like a volatile memory using CPU load and store instructions. But also it retains its content across power failures. So the term non-volatile memory refers to the group of solid-state storage devices from flash memory in SSD drives to battery-backed up memories. From this group, we can extract the devices which are byte addressable and are fast enough, so it is reasonable to delay a CPU load instruction, waiting for loading data directly from persistent memory device. So why do I mention this now? In July 2015, Intel announced 3D crosspoint technology. It is expected to be much faster and much more durable than traditional SSD and more denser than conventional RAM memory. It is also announced to be present in two forms: as an SSD drive and in NVDIMM factor. It is announced that in NVDIMM it will support up to 3 terabytes of memory per one socket. Here you can see the NVDIMM software architecture utilized by sample Linux software stack. So at the bottom, there is an NVDIMM device. This device is described to operating system by BIOS via structure called NFIT, which stands for NVDIMM Firmware Interface Table. This NFIT structure is defined in ACPI document. ACPI is an open standard that the operating system can use to perform discovery and configuration of hardware components. So beginning from ACPI 6.0, there is also included NFIT. These structures provide information that allows to enumerate NVDIMM devices and associate system physical addresses created by NVDIMMs. So above NVDIMM device, there is NVDIMM device driver, which interfaces operating system, file system, and the device itself. It allows to manage all NVDIMMs, and it is also included in Linux kernel beginning from version 4.0. Here we can see different functions of the NVDIMM device driver. On the left, we can see that it supports manageability software. At the center, there is a block support. Here, it allows block access using a file system and standard file API, or directly standard row device access. But the most interesting part is on the right side. It is a persistent mode. In this mode, driver exposes memory to operating system as a device. On such device, we can create a file system. So beginning from Linux kernel 4.0, there is included a DAX, which stands for Direct Access File System. The DAX code removes the extra copy that the extra copy to the page cache by performing reads and writes directly to the storage device. So with this file system, we can create a disk. On this disk, we can create a file. And then, in our application, we can use the mmap to mmap this file some range of memory in our application. So once our application has access to some range of memory, then we can use this memory directly and performs loads and stores directly without the driver. But the mmap function gives very raw access. It returns only the address, and later on this address we can use sbreak system call, which allows to create malloc and free functions. But we must be aware about some limitations. For example, when the program allocates some range of memory, but dies before linking it to anything, we have a persistent memory leak. So we need some kind of PMEM-aware version of malloc. And this is a place for NVML, which is a non-volatile memory library. This library helps developers to manage some common problems like memory allocations and transactional updates. It is a user space library, so it operates outside of the kernel, so it's faster and more efficient. It helps also with some other issue, because we need some kind of msync to flash data from the cache of CPU and persistent memory device. There are two instructions introduced, which is clflash_opt, which push data out of the processor cache, and pcommit, which commit all outstanding changes to the persistent memory device. And both these instructions are included in non-volatile memory library code. So this library can be found on pmem.io webpage and also on the GitHub. It consists of 6 libraries, including libpmemobj, the most important one. So with this library, we can create a memory pool with dedicated function pmemobj_create. Reference to this pool is then passed to other functions. We can take advantage of, we can use atomic allocations, or we can take advantage of transactional API, which will execute series of operations in a transactions. Objects created with this function are represented by structure called pmemoid, which consists of unique pool ID and offset inside the pool. We also can assign some type number to the objects allocated and then iterate through all the objects inside the pool. So we decided to modify Redis using this architecture and this library. So we decided because this is the most popular key value store on the market, and modification is relatively easy. So what we did is we separated user data which are now stored in persistent memory, and Redis internal data, which are still stored in RAM. And things like a dictionary hash table is still placed in RAM and can be rebuilt at a startup. So persistent memory mode is configured via parameter in a config file, and when we enable persistent mode, the RDB and AOF modes are disabled because they are no more needed. The persistency is supported by persistent version of Redis. We know that it is hard to be faster than Redis on RAM, but we can compete with persistency modes of Redis. So we tested different scenarios on 2-socket 16-core machines with 256 gigabytes of DDR3, part of which was exposed as normal RAM and the rest as a persistent memory with NVDIMM driver. For AOF and RDB modes, the storage was 800 gigabytes Intel SSD attached via NVMe interface. So here we can see some results. The results are the number of operations per second, and we tested different object size. So here we inserted 500,000 objects to the database. And we can see that the persistent memory version is, which is, green, yellow on this diagram, is 50–60% slower than RDB, but it is also 2 times faster than AOF, the orange one. But I should also mention that in this configuration, the RDB snapshots were triggered every second. And AOF was configured to trigger fsync after every command. But the persistent memory version provides the consistency on the command level. So it is much better than RDB with snapshots after every second. And it is quite similar to AOF mode. Here, the persistent memory version is slower than RAM because we use NVML for providing consistency of the commands, of the data, and for keeping data in a consistent way. But the number of operations is only one scenario. There are some other features that we can also compare. For example, there is a startup time. Here we can see that the startup time for persistent memory version is always the lowest and almost independent from the database size, around 1 second. For RDB and AOF, it is several times slower. For persistent memory version, this time could be 0 second. But in our modification, the dictionary hash table was rebuilt at startup. Here we can see the usage of DRAM in the system. So for size of data set around 5 gigabytes, the AOF requires around 8 gigabytes of RAM. For a persistent memory version, we need around 10 megabytes of RAM. So we really need much less RAM in our system. we also checked what happens when the size of dataset grows up to the whole available RAM in the system. So for version of Redis without persistency, when the size of dataset was at around 90% of the whole available RAM, there was a drop of the performance. With RDB and AOF, the drop of the performance was observed at around 50–60% of the available RAM. And for persistent memory version, because it doesn't use RAM, it stores data in a separate device, the performance is stable, and even when size of dataset is around 150%. We already know the results for running one instance of Redis, where the persistent memory version was around 2 times faster than AOF. But what happens when we were running 4 instances at the same time? So for persistent memory version, there was no difference in performance. With AOF, we observed the difference in the performance, and it was around 10 times slower than persistent memory version. When we were running 10 instances at the same time, the persistent memory version was around 50 times faster than AOF. So AOF here is, I think it's light green or yellow color at the bottom. And the persistent memory version for the bigger objects is 15 times faster. The difference comes from the fact that AOF uses system calls, which triggers file system and I/O operation. With persistent memory version, we don't use a file system and a kernel code. So can we say that Redis is ready for a persistent memory? Actually, there are some constraints in persistent programming model. For example, Redis uses a fork function. When a process executes fork, parent process pages are marked as read-only. And when some of these pages are modified, the copy-on-write mechanism duplicates those pages. With a persistent memory architecture, there is nowhere to duplicate these pages. So there is no second pull where we can duplicate them. We can say that fork is not needed for persistent memory version because we can disable AOF and RDB modes once we are using persistent memory version. But in Redis, there are still some features like replication that requires a fork. So I invite you to visit and contribute to this GitHub repository. And I think we are running out of time. And if you have any question, please don't hesitate to ask. Thank you. You are asking about the performance of or the latency when we are using a replication with a persistent memory version. So, as I said, the original replication is not able to be managed with a persistent memory version because of some constraint of the architecture. But the NVML library provides a feature called remote replication also. So it is replication, a pull on a remote node. I don't have benchmarks of this replication right now, but I can provide them later because we already did some tests on it. So we are asking if it is possible to access the memory pool when the Redis is running. So this is a read-only access, right? Yeah, of course you can access and copy this. Yeah, but you must be aware about this is still updated, so yeah.
Can you snapshot it anyway?
Yeah, you can create a remote replication, a second pull, for example, which will be updated automatically with NVML code.